This video covers estimation and from chapter 10. So in chapter 10, you're not going to skip the case studies. And this is important because you need to start getting some practice with working with data sets in Excel. And you'll also be using PAST to solve some of the questions, specifically the ones in the case studies. So here we have, this is Lane's book, so his online stat book. To get to a case study, like notice these first questions here, 24 through 28, etc., those refer to the Angry Moods case study. All right, so to find them, you can click here on the Angry Moods link. There's a description of what the study is. This tells you what some of the variables are and what they mean. And then to find the data, if you scroll down to the end, you want to use Open Data with Excel. So Lane has a statistical analysis software in something called Analysis Lab. Usually people have trouble getting this program to work on their computer. And so we're going to just use PAST for all analysis of data. So to get the data, you would hit Open with Excel. And then what's going to happen is it'll download onto your computer. And then you can open up the file like this, hit Enable Editing, and then work with the data. All right, so maybe we'll play around with that later on. So I'll go ahead and just leave this open on the desktop for now. All right, so estimation is all about predicting what will happen, or what a mean could be. All right, so let me just give you a scenario here of what estimation is all about. All right. Okay, so here we'll start with one of our familiar biological examples. So what if I'm, interested in these Gulf fritillaries, and let's just say nobody has studied them before. So I go in there and I collect about, 9 or 10 of them, something like that. I think we have an actual size here. So we'll go out, we'll collect a sample of 9, and we measure all the butterflies in that sample, and then we find out a mean. Notice I've used a regular M here instead of the Greek symbol. So this is a sample mean, all right, based on these 9 butterflies. Now, for this example, we're going to say that we know what the standard deviation is in these butterflies. As you're probably guessing, that almost never happens in the real world. So, it's very rare that we actually know what sample standard deviation, population standard deviation is. We usually don't know this. But it's useful for illustrating how estimation works. Okay, so what we have here, this 90 millimeters, this is think of that as an estimate of the population mean, because that's what it is, I mean, without any other information, somebody comes up to you and they say, well, how big are these butterflies? Well, one thing you might give them is an average, right? So an average is what is called a point estimate. So yeah, that's valuable information. It tells us approximately how big these butterflies are. But remember, it's only based on our sample of 9. We can actually do a little bit better than a point estimate with something called an interval estimate. All right, and that is what this whole chapter is about. So what you're going to be doing is generating interval estimates. All right, well, let me explain how these work. All right, so I think I can illustrate this best by looking at Lane's calculator for normal, his normal, inverse normal calculator. Okay, so let's go here to the inverse normal calculator. All right. Okay, so what we have here, that's of course the standard normal calculator. But what I'm going to do is I'm going to just make up something. Let's say, okay, remember we measured those butterflies, and in our little sample, the mean was 90, right? Well, that's probably not correct. Let's just say that the real mean out there is 92 millimeters. So that's what the population mean is. We don't know that. Remember, that's something we're trying to estimate. So what we find that our estimate is pretty good, based on what we were working with. All right. Now remember that we're dealing with a sample here. All right. So we're dealing with a sample. We had 9 individuals. That's what that estimate was based on. So let's make a sampling distribution. So you know this from the last chapter. A sampling distribution would be the standard deviation over the square root of n, right? So for this one, of course, the sampling distribution is going to be 36 divided by the square root of 9, which is 3, of course. So the standard deviation of the sampling distribution, or the standard error, right, is going to be 12. So I'm going to try and model what this might look like. Okay. Now, what we're going to do is we're going to generate something called a 95% confidence interval. So I'm going to just shade 95% of the distribution here. Okay. All right. Now, what I've got on the screen here, this is a model of the population of all the Gulf fritillaries in the world. So remember, what we've tried to do is we've tried to estimate that mean there of 92. Now, in our sample, we got 90, which is over here. All right. Now, what if we go out and we collect another 9 butterflies and we come up with a sample? Well, we might get one that's a little bit higher, right? Like 103 over here. Now look what happens if I change, so that would be like our sample mean. So now what I'm going to do is I'm going to put in a sample mean. Remember, the population mean is 92. So just by chance, I'm usually, if I'm randomly selecting these, I'm usually going to get individuals from here. Yeah, I might get one of these small ones or one of these large ones, but that's only going to happen 5% of the time, right? Because 95% of the time we're going to be picking things in here, or we're going to estimate means in here. Remember what these are on the bottom here. These are means that have been generated from samples of 9 taken from the population. Okay, so the first time around, right, in our sample, we got 90, okay? Now look at this interval here. So from here to there, you see that interval, 66.48 to 113.52? Notice that that includes the population mean, okay? Now we go out and we do this again, all right? Let's say this time we happen to get a few large ones. Maybe we'll get 103, as that's, pretty far. But look at the interval again. See how it includes the true population mean, which is down here at 92? Now we might do it again, and maybe just by chance. So let's look at this, what this thing really looks like. So here's the real distribution. All right. So we're going to go out, collect, 9 of these things, come up with a mean. 95% of the time, the mean is going to be somewhere in this area. So even if we get a low number down here, like 70, let's see what happens. That's on the low end. What if that happened? Well, look at that. We would still have 92 in the confidence interval. Let's go back to it one more time. All right. Again, remember, it's usually going to fall in this thing. So what if we got one on the high end? Like if we happen to catch a bunch of big ones just by chance. 115 this time. It's like, see how I'm like slide this thing, 92 is still in there. Okay, so what you should be seeing here is no matter what mean we get, we're going to enclose okay, so, oh well, all right, first let me tell you this. So occasionally you're going to get a value over here or over here. And now here's the important thing. How often are you going to get a mean over here? Well, only about 5% of the time. All right. So if we got a mean over there, like 58, we would really have to be unlucky. And then 92 isn't in there. All right. So what that means is with a confidence interval, 95% of the time in an interval like this, you're going to get the population mean. Okay? So now let's go back to the sample we were working with. So let's look at that again. All right. So here we have our data, our problem here. So again, we don't really know what the population mean is, but we do have a sample of n equals 9. That's how we generated this estimate of the population mean. Remember, that's a point estimate. But an interval estimate would be better. So what we can tell people is we can say, all right, I'm going to generate an interval that's going to include the mean, the population mean. Now that's what we have done over here. So what I've put in here is I've selected the area I'm interested in 95% of the time, right? I put in the sample mean, and I put in the standard deviation. Okay, I'm sorry, the standard error. So that's the standard error, because remember, this is based on a sample of 9. All right. What that confidence interval means there is that 95% of the time, the population mean is going to be somewhere between 66.48 and 113.52. So this is actually the answer that we could report. All right. So there would be two ways to tell people what's going on in these butterflies. One would be to give an interval, a point estimate, 90 millimeters. That's just based on a sample of 9. But we can do better if we can tell somebody something like, let me see where I put this. Yeah, here it is, what the confidence interval is. All right, so how would you do that? So you would say that the population mean, notice I'm using the Greek letter mu for the population mean, is within 66.48 and 113.52. That is what's called a 95% confidence interval. Okay? Now what if we wanted to even have a more inclusive interval? So, for example, a 97% confidence interval. We can get that by simply changing this to 97%. All right? And then that gives us a 97% confidence interval. Another commonly used confidence interval is a 99% confidence interval. There's a 99% confidence interval. Okay? Nobody ever reports a 100% confidence interval because you can't, 100% is basically from 0 to infinity, and, that's that's not very useful to people. All right, let's see now. So we found a confidence interval. This is a 99% confidence interval. More often than not, you see 95% confidence intervals. Later, we're going to see that's the only thing that PASS generates. It doesn't even generate 99% confidence intervals because people almost never use those or report those. Okay, now there's another way to find a confidence interval with data like this. And let me show you this, okay? So let's go back to the standard normal distribution. All right. So here we have, So here we have the standard normal distribution. Remember, has a mean of 0 and a standard deviation of 1. Okay. So 99% of the standard normal distribution is between negative 2.576 and positive 2.576. And then 95% is between negative 1.96 and positive 1.96. Okay, so you may remember in the last chapter, we saw that any normal distribution or values on a normal distribution can be transformed into values in a standard normal distribution. So we had that z transformation. So what these numbers are here, these are z-scores, all right? And I may have even mentioned last time, they're actually called critical scores or critical values. So another way to generate a confidence interval is to multiply these critical values times the standard error and then add it and subtract it to the mean. Okay, so let me show you what that is mathematically here in the PowerPoint. We have an example of that. Okay, here we go. All right, so this is a different approach, and sometimes this is easier. Now, you have to do this with some types of data. I mean, with a normal distribution, we can usually, if something has a normal distribution, we can usually model it by, using Lane's calculator. But you should learn how to do it this way as well, because you have to do this with some applications. All right, so a different approach is to, uh, multiply those critical values times the standard deviation. All right, let's see. And that sort of summarizes how we found that. And then the interval, like here's a way to do it. You would take, like this is with the same data we had before. So you could take the mean plus or minus the critical value times the standard error. And that gives you those same scores. So you could try that with the calculator. Let's see how that works there. All right. We'll open up a calculator. So actually, we'll bring this up for comparisons here. All right. So you may remember we first found the the 95% confidence interval directly this way. Let's just try to find this upper limit using a calculator and that formula. All right, so we'll open up the Google calculator here. All right, so let's see, we have the mean, 90. All right, and we're going to add that to the standard error, which was 12, times the critical value, 1.96. All right. Now that formula is going to give us the upper value of the confidence interval. All right? And there you have it, 113.52, which as you see here is the same thing we found this way. Now to get the other one, you just subtract that value. So sometimes if I'm doing all this with a handheld calculator, I'll just play around. I'll kind of go back to, usually I'll find this part of the equation first, but you can kind of go back to where you were. So let's just subtract 90 from this. All right. So what that is, that's that correction, if you want to think of it that way. This is the confidence interval. No, I'm sorry, the standard error times 1.96. Now, if we want to subtract that from 90, you can kind of do that, rather than type it all again, we can just subtract 90 from it, and just remember that this is positive. See, that's that same number that you have there. Okay, so a lot of times I'll do that. Otherwise, you end up, punching all the numbers in the calculator 2 or 3 times, and you're more likely to make an error somewhere when you do that. That's just a little shortcut that I use all the time. Okay, so far what we've done is we have found 95% confidence intervals when the population standard deviation is known. Okay? Now, you may remember that when we're working with correlation coefficients, right, like Pearson's are, they don't have, their sampling distributions are not normally distributed. Remember this? Instead, they're this skewed sampling distribution. So if you're trying to generate a confidence interval around Pearson's R, what we have to do is first make a confidence interval around Fisher's Z and then convert back to R. Okay, so let's do a little example of how this would be. Okay, so here's an example. All right, so we have a sample correlation coefficient of 0.6. So let's say that's like the height and weight in our class again, and that's just our class. What we want to do is we want to extrapolate. We want to say, based on this data from our class, how does this compare to the population? So if we wanted to give a confidence interval for this correlation in Broward College, for example, what will we do? All right. Well, as I was saying, we've got to first convert this to Fisher Z values. So you may remember we use the Fisher Z calculator in PASS to do that. So that's this calculator. So we would start out by putting that in here, 0.6, all right? And then there's the Z-score, okay? Now, the Z-scores, remember, those have a normal distribution. So once we've got that, we can generate a confidence interval the same way we did with the other ones. So there's actually two ways to do it, again, all right? So let's first take a look at the normal distribution here. So 0.693, I'm sorry, inverse normal, right? Okay. So if we wanted a 95% confidence interval, all right, we need the mean. Okay. And now we're going to need the standard deviation. Okay. I'm sorry, the standard error, right? So you may remember for Fisher Z, the standard error is 1 over the square root of n minus 3. So for this example, we had 28. So 28 minus 3, of course, is 25. So 1 over square root of 25 is 1/5, which is 0.2. Okay, so we could put that in here. All right, 0.2. Okay, and then hit, oops, something is wrong here. Let me see here. Why isn't this working? 0.693. What is going on? That should work. Let's see. Let me try that again. Inverse normal distribution. Okay, let me try that again here. Oh, Lordy mercy, what happened to everything? Calculators. Okay, inverse normal distribution. Alright, so we want a standard deviation of 0.2. Oh, I'm sorry. Yeah, no, that's right. That's 1/5. Okay. Mean of 0.693. I probably put one of these numbers in the wrong place. And we want 95% of it. Okay, let's see. There we go. Okay, so that should be the 95% confidence interval. Now, let's work it the other way. That's what I have here in the PowerPoint. So let's take a look at this. So like another way to do it. All right. Remember, you've got, this, here's like the formula for the confidence interval. So to get the lower value of Z, we would take Z minus that critical value, 1.96, because remember it has a normal distribution, times the standard error of Z. And then here's the upper value. Okay? All right. So now we've got a confidence interval around Z. Those are the same numbers we found using the normal distribution directly. So notice there's two different ways to do that. All right. So we can do that as long as we're working with that normal distribution. If we're not working with that normal distribution, like with a t-distribution, you have to use this method. So that's why we want to talk about it now. All right, now, once we have this, though, we're not really done, because what we want is we want a confidence interval around R, not around Z. So, if I'm trying to tell people, what is the correlation of height and weight at Broward College? we got this data based on our class. There's our point estimate, but we want to give people a 95% confidence interval. We've got to convert these two numbers back. So to get them back, we just go back over here to Lane's calculator for the Fisher's Z calculator. And we notice down here we can go the other way. So remember the lower value I think was 0.301, right? And then you hit convert. That tells you what the lower correlation coefficient is. Okay, so putting those in, you take both these numbers and put them into that, you should get the population correlation coefficient. This actually is this Greek symbol rho, which I'm just going to call rho like that. It looks kind of like a P, and it's sort of hard to read, and people think it's probability or something, but it's actually the parameter for the correlation coefficient is rho. So what this is saying is that if, based on our sample from our class, we can be about 95% confident that on at Broward College, the correlation between weight and height is somewhere between 0.292 and 0.795. And that, it's a pretty wide interval, but at least we can see that it's positive. It's not negative in this particular interval. All right. Okay, so let's see what else we have here. So here we have another practice. I think we can skip over that one because we just went over it. Let's talk about with a proportion. What do you do if you have a confidence interval around a proportion? Well, this one also has sort of you may remember we can get these sort of things by using a normal approximation. Now, you remember the rules of thumb we had before? So, sometimes when you have a lot of skew in a proportion, like remember if it's a binomial distribution, so when you're working with real low values like 10% and high values like 90% populate, then you get these sort of skewed distributions that aren't really normal. So we have to kind of take that into account, all right? So the formula for this is that thing, all right? Now let's see what we've got there. All right, so what we have is our proportion. So let's say if we wanted like a confidence interval of a proportion and our sample was 70%, then you'd have 70% here, plus or minus. Now this is the critical value we've been using, like 1.96. And then here is the standard error that we used before. So you may remember we were using this in the last section where you have, so it'd be like 0.7 times 0.3 divided by your sample size. So if you got that proportion based on 30 individuals, you put 30 there. Then there's this little thing. So this is new. Now you may remember in the key to chapter 9, Lane mentioned something called the correction for continuity. That's what this little thing is. So it's possible. The thing is, we have to use this because there's no way to generate a 95% confidence interval using a binomial distribution. You just can't do it that way. Or at least there's no easy way to do it. And so instead, what we do is we put in this correction for continuity. Now, if you look at this, see how you got in the denominator here? What that means is this is going to be pretty close as long as you have really big sample sizes, because when the sample size gets really big, this gets really, really small and doesn't affect things very much. Okay, so again, it's use a slightly different formula, but we're still working with a normal distribution. Okay, all right. Now, what do you do though when you don't know the population standard deviation? And this is the way things really are normally going to happen. So, if you're working with a proportion, we use the normal distribution approach. even if we don't really know what the population standard deviation is, we still use this when we're working with a proportion. Same thing goes with our correlation coefficient. Remember, we were just looking at the correlation coefficient over here. Let's see, where was that again? Oh yeah, here we go. So you see here, we're like generating a correlation just based on our class. Does this say anything about knowing what the population standard error is? No, it doesn't, does it? So even though we don't use it, we still use this Z method. This has a normal distribution. So, we can find what its standard error is. Okay. Um, the situation when we don't know would be like, for example, if we went out there and we measured those Gulf fritillary butterflies, but we didn't really know what the population standard deviation is. What do we do then? Well, if we usually, and this is usually the way things are with that type of data, we usually don't know what population standard deviation is, so we can't find, the standard error. We can't find that. Instead, what we use is something called the student's t-distribution instead of the normal distribution to generate confidence intervals. Now, over here, we have some drawings of t-distributions. The thing about t-distributions is, how like a normal distribution, it's really defined more by its like mean and standard error or standard deviation. With these things, yeah, they're defined by parameters like that, but they change their shape substantially. So sometimes when you have small distributions, they're real pointy in the middle. This is called strongly leptokurtic. And then as the sample sizes get larger, they get closer and closer to normal, but they always are a little bit leptokurtic, meaning they're not perfectly normal. They're a little more pointy in the middle and a little wider on the ends. So they have slightly different shape. Now, you know how Lane provides us with that nice little calculator that allows us to sort of visualize the way a normal distribution looks? These, we don't have a calculator that will generate a t-distribution for us. You can find pictures of them online, but we can't shade it in. So we sort of have to think about what we're doing, all right? Okay, the good news is that we use this same type of formula. So here we have a formula for generating a confidence interval when we don't know what the sample standard deviation is. So let's say we wanted to work with those butterflies. So we know that the mean is 90, but we don't know what the standard deviation is. Well, we could estimate it by taking, using the Excel to generate a standard deviation or something like that. And then we would use this formula where we have the mean plus or minus a critical value again, but this one is not a critical value from a normal distribution, it's a critical value from a t-distribution times a standard error. Okay, so that's pretty similar. So you have a mean plus or minus a critical value times a standard error. We'll see some examples of how to do this in a minute. Now, finding these critical values, these change depending on your sample size. So with a normal distribution, no matter what the sample size is, the critical value for a 95% confidence interval is always 1.96. That is not the case with a t-distribution. With a t-distribution, it changes, and we find them using something called degrees of freedom. And a degree of freedom for like a single sample would be n minus 1. Okay, we're going to see how all this is done. It'll be easier to follow if we look at an example. Okay, so here we have an example. So this is just like the butterflies. All right, so let's say we go out, we catch these fritillaries, and we're not living in this magical world where we actually know the population standard deviation. We don't know that. So we go out, we get a sample of 9, all right. We have the mean of 90 again. This time we have to like generate a standard deviation. So we estimate the standard deviation of the population at 10. Okay? How do you generate a 95% confidence interval with this? Okay, well, let me show you. We're going to use that same formula. Whoops, hold on, I didn't mean to hit that button. Let me go back to where we are here. All right. Okay, so first of all, we're going to need a standard error. Now you find a standard error the same way we've been finding a standard error. You take the standard deviation and you divide it by the square root n. So in this case, we've got 10 divided by the square root of 9, which is 3.33333. I've sort of rounded that one off. Okay. The other thing we're going to need is degrees of freedom. Now, we're working with a single sample. We have estimated a single standard deviation. For that reason, we lose 1 degree of freedom, we say. So since we have a sample size of 9, we lose 1 degree of freedom. So to get the degrees of freedom, it's n minus 1 is equal to 8. All right. Now to find the critical value, this thing we get from one of Lane's calculators. Let me show you where it is. Remember how we found critical values for a normal distribution using an inverse normal calculator? To get a critical value for a t-distribution, you use the inverse t-distribution. Okay? See what I mean? There's no nice little thing here. But all we got to put in is the degree of freedom. So we put in our degree of freedom, and we lost 1. So we have 8 degrees of freedom, right, for a sample of 9. And then we pick the confidence interval we want. Notice you only have 3 options. You can do a 99% confidence interval, a 95% confidence interval, or a 90% confidence interval. There's the critical value. Okay, so this would be on the t-distribution. Notice it's bigger than we had with a normal. Remember, the normal distribution was 1.96, wasn't it? See how that one's bigger? Okay. I wonder what happens if you increase degrees of freedom. What if we had 10 instead? It went down a little bit. If you get bigger, 100. Now we're getting almost to 1.96. But unfortunately, we don't have a very big sample size. No matter what, though, the confidence interval generated from, when we don't know the population standard deviation, it's always going to be bigger than a confidence interval we would get from a normal distribution. And that is because there's a new level of uncertainty. The uncertainty is we don't know what the population standard deviation is. Okay, so let's go back to our example here and pick up where we left off. All right, so we found the degrees of freedom. It's n minus 1. And then we looked up this critical value from Lane's inverse t distribution. All right. Now to generate the confidence interval, you use the same formula like we had before. So the population mean is somewhere between the sample mean minus the critical value times the standard error. All right. And the sample mean plus the critical value times the standard error with 95% confidence. Okay, so if you pop all that into a calculator, this is what you should get. All right, so I'll let you guys do that on your own. Okay. All right, so here we have a caution for you. For a sample, you usually first calculate the sample standard deviation or the variance, and then calculate this. Okay? So don't plug sample standard deviations directly into this. Remember that this is standard error in this formula, not standard deviation. Sometimes students will take the 10 and put it into this formula. That gives you the wrong answer. All right. So you have to find the standard error before you can proceed to making a confidence interval. Okay, let's see. More practice. So what do you do if you have actual data like this? And this is the kind of thing you're going to be doing with those case studies. So here I have a little sample that I went and took. I don't know what these could be. One was 2, 3, 5, 6, and 9. I want to generate a confidence interval for the population mean. What do you do? Okay. So these could be measurements of something we're interested in. Popcorn, I don't know, whatever. Uh, okay, so usually I would use Excel to calculate all that stuff just because I don't like putting, entering things into the calculator too much. All right, so let me see. We had an Excel open a minute ago. Let's see here. Oops, that's not what I wanted to do. Let's put that back up there. Here we go. All right, let's just open a new one here. New. All right. Okay. So what I'm going to need to do is I'm going to need to first put this data we had into that spreadsheet. All right. I'm going to play around with all these windows here. There we go. Now I can see everything. All right. So we've got 2, 3, 5, 6, and 7. Okay, so I'm going to need a mean. So we can do it. We can take it from there with the Excel. So I'm going to enlarge this so everybody can see what's going on. Okay. So we're going to need a mean. We're going to need a standard error, right? And we're going to then generate our confidence intervals. So I'm going to put the upper limit here, and I'll put the lower limit here. Okay. What do we do? Okay, let's see. So for the mean, we can just get Excel to calculate all this for us. Let me, we'll go ahead and enlarge this a little bit more so y'all can see. All right. Okay, there we go. So you can just enter in actually that's a little bit too big. Let's go back. Let's try 150. Maybe then you can see things a little better here. All right. Okay, let's see here. Everything should fit in there. So to get the mean, you just put average. All right. A1 to A5. Okay. All right, there's the mean. Okay, so what is the standard error? Remember, the standard error is the standard deviation over the square root of n. How many data points do we have there? We have 5 of them, right? Okay, so to get the standard error, it would be we need the standard deviation, which is STDEV. All right, and then you have A1 to A5. All right, and then we're going to divide that by the square root of n, which is 5, right? Sometimes putting all these formulas in can be tricky, and then you got to make sure you got all the parentheses and stuff. Yep, messed it up, but there it is. That's right. Okay, that's what I want. Okay, so there we have the standard error. So now let's see. To get the upper and lower confidence intervals, we are going to have to find out what the critical value is. Okay, since we're working with a single sample, we lose 1 degree of freedom. The degrees of freedom is n minus 1. Okay, because we're estimating a single standard deviation here. All right, so let's see here. Let's bring up Lane's calculator here. All right, so we have 5 data points, so that means we only have 4 degrees of freedom. All right, there's the critical value, 2.776. So I'm going to just copy that, hit Control-C to copy. Now I can go back to my spreadsheet. All right, so let's see. I'm going to just put the formula in here. So remember, the upper value is the mean, so A6, all right, plus we want the standard error, which is A7 there, all right, times the critical value that we just looked up. So I'm going to hit Control-V to put that in here. Okay. All right, so there's the upper value. Now, to get the lower value, we're going to subtract that. So I think probably going to be hard to do that way. Let's just do it this way. A6, all right, minus, all right, we have A7, okay, star, and then I'm going to put in my critical value. All right, there's the lower value. So what that means, you know, and you have such a small sample size, that's one reason why this confidence interval is so wide. We could say that the population mean of this sample is somewhere between 7.174 and 2.026. By the way, I'll show you a neat little trick. You can get this to round things off for you just by narrowing the column to the number of decimals you want. Isn't that neat? Okay, that's something you can do when you're taking tests and stuff. All right, now let's see here. So I have that same thing worked out here in the PowerPoint. All right, so this is, you could do this with a calculator, handheld calculator. You can do it with Excel, whatever works for you. As you see, I've got the same answer here. Looks like I've rounded things off a little bit more. I may have made a mistake. Let me see here. That looks like the right critical value. Let's see. Where did I get this standard error? I bet I did something wrong here. Let me see. 956. Okay, let's see what happened. Oh yeah, look at that. I put a 7 there. That's supposed to be a 9. Another nice thing about Excel is if you make a mistake and you catch it, you can go back, just change the number, and excuse me, everything else will change automatically. All right, and I was gonna round this off again. Okay, well that's good enough for now. Okay. All right, so now we have the right numbers in there. Okay, so this would be the answer. And this is usually how people report confidence intervals like that. You know, this tells us the population mean is somewhere between 1.6 and 8.4. All right, let's see here. So let's look at another situation. All right, so difference between means. All right, this is a common instance when we might want to find a confidence interval. So again, we talked about corn plants before, where we had some that were fertilized and some that were unfertilized. We could go out, we can measure certain sets of these, we can, find the means. We can also estimate the standard deviation, right? So we can do that, all right? Well, look at the confidence interval for a difference between means. Notice we find the difference between the means, right? And then we have, same thing we've seen before, critical values times standard errors. All right? Now, here's the thing, though. When you're working with two samples, the thing is we actually estimate two different standard deviations. So we have because we have two different groups, right? And each one is like an estimate of the population standard deviation. So we lose a degree of freedom for each one. All right, so in other words, if we had 20 plants in one group, we're going to sort of estimate a standard deviation for that group. We would lose a degree of freedom. And then in the other group, we also had 20 plants, we would lose one. So we'd wind up with like 38 degrees of freedom. Another way you can look at it is degrees of freedom are like all the plants in the study. So if you have 40 plants total, you'll lose 2 degrees of freedom, 38. Okay. We calculate the standard error the same way. So it's the square root of the standard deviation of the first group divided by n minus 1 plus standard deviation of the second group divided by n2, whatever. Now, here's the thing. This is where we're going to diverge a little bit from what we were doing in the last chapter. You can only use this approach when the sample sizes are equal. All right? So if the sample sizes are not equal, then we're going to use past. And that is because this standard error, you can't use it if the sample sizes aren't equal. You have to generate something called a harmonic mean, which becomes a real pain to calculate. Okay. All right. So, well, let's look at an example. Let's see here. What do we have? Okay. Skip over that for a minute. Let's see. We've done this already. Oh, I don't have any in here. Okay. So let's see. We'll generate an example of how we might handle this kind of thing. All right. I'm just going to make one from scratch. Let's see. New slide. All right. And I'll put it in this PowerPoint for you guys so you'll have it handy. All right. In our control plants, the mean is, let's say, 120 millimeters, right? Plants treated with fertilizer are 130 millimeters. And these are sample means, okay? All right. What we want to do, and for this, let's make it 20 for each group. Okay. Let's see. And we also are going to need a standard deviation. All right, so we'll say S equals, how about 5 for each group? Okay. You know, sometimes if you had, well, you could work with different ones that should work fine, but we'll say 5 millimeters for each group. Okay. So we're going to generate a 95% confidence interval on the difference between the means. Let's say the population means. Okay, what do we need? All right. Well, we're going to obviously need a difference between the sample means, right? So we have M, we'll call it M control. No, I'm sorry, M fertilizer. Let's make it positive, all right? So M fertilizer minus mean of the controls, all right? What's that equal to? That's 130 minus 120, all right? And that's equal to 10. Okay, that's the difference between the means. Should make things easy. We need our degrees of freedom. All right. So in the case this time we have 40, so the degrees of freedom is going to be 38, right? Because we're going to have to estimate two standard deviations, or we have estimates of it from each. For this example, I just made them the same. Now, if they were different, you know, you could put in different numbers, but let's just keep it the same for now. All right. So we are going to need a standard error. Now remember what this is. This is the square root. I'll just do it like Excel does. All right. Actually, I have a little formula I can insert, so I'll go ahead and do that. Insert symbol. All right, this one. All right, so we're going to need the square root. All right, of S fertilized squared, let's see, plus S control squared over N. All right, because, you know, it's actually the two things separate, but when you add them together, as long as the N's are the same, it's going to always be in the thing there. All right, so what that's going to be That's going to be the square root. I'm going to like insert that again. All right. So we have 25 plus 25 over 20 in each group, right? All right, so that's going to be square root of 50 over 20, or square root of 5 over 2. Okay, let's see what that is. All right, so we'll bring up our calculator here. Square root 5 divided by 2. All right. Okay, so there's the standard error. All right, so I'm going to go ahead and I'm going to use that in a calculator in a minute, but for now I'm just going to leave it in here. All right, so let's see what we've got here. So that's the standard error. All right, now the other thing we're going to need is our critical value. Could call it, yeah, how about t-crit? All right, so what that is going to equal, we'll go back over here. We can go to the inverse t distribution. This is where we put in our 38, right? And we're interested in a 95% confidence interval, which is the default. Here's the critical value we're going to use, 2.024. I'll go ahead and put that right here. Okay. Now, let's find the upper limit. All right, we'll do that first. So I've already got this standard error in my calculator. So I'm going to have to remember what the formula is. We're going to have this difference in means added and subtracted. You know, we're going to add and subtract the product of these two things. So to save time entering numbers, what you can do is now that we've already found that, I can just multiply it by this. So I'm going to go back over here and I'm going to multiply it by 2.024, I think it was. Hope that's right. Let me make sure before yeah, that's right. Okay. Okay, so this is what's going to change. All right, so remember what we're going to do is we're going to take the difference in means, which is 10. We're going to add this to it, right? So that's going to give us 13.200. That's the upper limit. And then we're going to subtract that from 10. Okay, so we can go ahead and even write this. Let me just, we'll do this one first. Just remember this is positive. So 6.780. All right, so let's see. That's the lower limit here. 6.780 is less than the difference between means. So I'm going to write this formally here. All right. We'll use this little thing. Okay. All right. So we've got, we'll call this mu f minus, all right, insert symbol. Mu c, okay, and that is less than 13 point, now let me go back and find out what it was again. All right, so we can just go back to where we were. That's where we were, okay. So we're going to add 10 to that, 13.200, okay, 0.200. All right, so this is a 95% confidence interval around the difference between means in our controlled, our control plot. Okay. One thing that tells me, if you look at this, is at least 95% of the time, the fertilized plants are always going to be larger, because see how these are both, positive numbers? Okay. All right, so with that, I think you should be able to work the exercises in Chapter 10. So give those a shot at this stage. Remember to work through all of them, including case studies. Oh, I need to show you how to use past on this. All right, so for past, all right, let me see here. We'll close this one. and open up one of the other things here. All right. So the thing about these is they have different sample sizes. So let's try and first, I need to show you guys how to sort. I think we've done this before, but do you see how you have this category on the far left for gender is equal to 1 or a 2? So one of those is a boy and one is a girl, and I forget which is which. You have to look back at the case study in Lane to find out. But let's say I want to sort all these other scores over here so that I have boys and girls separate. All right. So you hit data, and then you can collect sort here. Now you can pick whichever column you want. All right. So we're going to sort on gender. All right. So notice now I have all the boys together and all the girls together. And to keep track of them, you can even like shade them just so you don't accidentally copy paste the wrong thing. So I'm going to shade the boys yellow. All right, group 1. All right. So what if I wanted to determine a difference between means for like anger expression? Are the boys more aggressive than the girls? I'm assuming that I've got these sexes right. I don't really know. All right, so what I would do is you sort of select all the boys here. So I've selected it. I hold the control key down and hit C. Okay. And then I go to past. Do we have past on here? Oh, I haven't downloaded it onto this desktop. With that, I think I'm, rather than, well, I can go ahead and do it really quickly. I think it's fairly fast. Let's see here. All right. Okay, let's see if you haven't already done this. Let's go ahead and show you how to do it. So remember, we're going to work with the most recent example of this. Downloads. I wonder if that's it. Let me see here. Probably. Okay, well, I'm going to have to stop this and get passed onto the computer. So I will stop this video and then I'll make another one showing you how to use this once I get past installed.